Welcome to this video outlining the beginner's map of electronics. If you have ever wondered where to start your learning journey in electronics, this is the video for you. Electronics is a fast-paced field, and it can be hard to know how circuits have been designed, but we aim to answer some of these questions. We will start by making a journey through analog electronics, then delve into digital electronics and logic design. From here, we can start exploring AC signals and understand circuit components through the electric and magnetic fields behind them. This leads to the more interesting concepts like signal processing and control, a crucial aspect of systems engineering. Then you can start exploring the age-old question, how do computers work? Nonlinear components are more advanced for this beginner's roadmap. Analog electronics is a wide branch of electronic engineering. It contains many things you will have learnt at A-level, such as Ohm's law, KVL, and KCL. This becomes the basis for techniques to understand circuits where there are many more variables at play. For this, we require loop and node analysis, law of superposition, and circuit equivalence. From here, you can analyze a wide variety of circuits and known configurations to begin designing circuits, including sensors. Circuits can be refined by considering noise analysis so that you can prevent unwanted signals, and understanding how the conversion between continuous signals and discrete signals helps with this, and much more. The outcome of this learning path is the ability to design circuits in real-world engineering and combine with digital electronics. The next stop is digital electronics. This may seem strange and abstract to begin with, as you start by looking at logic gates and Boolean algebra. However, the language of computers is binary, as it is represented by turning a switch on and off, which lends itself to digital circuits. Once this is understood, you can see how Karnaugh maps are used to design circuits, the main types being combinational logic and sequential logic. The latter is the basics of understanding computer memory. Logic gates and configurations can be changed with programming, so this allows you to understand how writing a script works. The outcome is designing digital circuits and combining with analog electronics. Electric and magnetic fields are the next destination on the roadmap. This area is much broader than we will consider here, but the main points to learn are how to derive the capacitor equations from Gauss's law in electric fields, and how to derive the inductor equations from Ampere's law. Other results from this topic are magnetic circuits and transformer, and electric generators and motors. But in electronics, we care more about the circuit components for now. The outcome of understanding this theory is to start understanding the capacitor and inductor components and the effect they have on the overall circuit. The equations to be derived are simple equations that contain derivatives, but become very important for setting up differential equations in future. Control theory and signal processing is next. This becomes more involved from an engineering maths perspective, so understanding how to solve ODEs is important to understanding this area. We can split the two signals into continuous and discrete signals. For continuous LTI signals, the Laplace transform can be used to convert a complex ODE into an algebraic manipulation, making it easier to solve. It reveals more about the system than we could appreciate by using standard methods for solving. The aim is to obtain a transfer function, a simple algebraic expression in Laplace space which encodes all of the physics of a circuit. You can analyze the transient and steady-state responses involved with things like charging up a capacitor and more. Frequency analysis is another result from this, where you can see how the gain of certain frequencies might be amplified or attenuated more than other frequencies. In a similar way, the Z-transform can be used to analyze discrete signals, where it is difference equations that need simplifying. The main outcome of this is in system design and engineering, and for use in controllers that might be used to optimize circuit behaviors. This could take the form of having a remote control car where the controller slows down the car at an optimal rate so it gets to its destination as fast as possible, but doesn't overshoot. Finally, on this beginner's roadmap to electronics is computer architecture. Here, you will find more satisfying answers to the question, how does a computer work? You will need to go through understanding the roles of the CPU and the ALU and how they work with memory to carry out the fetch, decode, and execute cycles. If you understand digital electronics and the need for being able to decode strings of zeros and ones, then you have an insight into the basic functions within a computer to perform a task. These lower gate-level functions are the building blocks of creating higher-level languages you may already be familiar with. Then, you can move on to understanding more about pipelining and parallel computation in order to make computation more efficient. Hardware descriptive languages, or HDLs for short, which are used to efficiently simulate digital circuits in more complex systems. Hopefully, this video has given you an understanding of the learning journey you should embark on in order to understand electronics. To start learning, check out our electronics playlists, which deliver the key concepts in shorter videos. Don't forget to subscribe to support this channel.